Okay, let's look at 2516. So if you look at the picture, we have, well, let's just read the problem. So it says a 7, so we're going to write our given find. So it says a 7.2 kilogram mass initially at rest, so the initial velocity is 0. And remember, we're going to chunk, we're going to read, we're going to write. String that passes over pulley. The string is attached to a spring, so they're going to give us the spring constant 300 newtons per meter that is initially unstretched. The incline is frictionless with an angle of 30 degrees. And this is important because all right. So determine the speed of the mass when it has moved 10 centimeters, which I'll convert to meters, and determine the maximum displacement of the mass measured along the incline. So first, let me kind of draw my picture. So I'm just going to do a rough sketch. And then I have my incline. So here's my spring, and then here's the pulley, and here's my mass. Okay. Remember, I want to have my frame of reference here. So if this is my frame of reference, if it ends up at the bottom, it makes a difference because this is going to end up moving 10 centimeters. Now this angle here is 30 degrees. So obviously from okay. So we're going to end up using conservation of energy. So conservation of energy in layman's terms says the total energy before is equal to the total energy after. And I can use conservation of energy between any 2 points. So I have to establish, am I going from here to here? So I don't know what this height is. So if this is my initial height, h naught, I need to find what that is. So this is a triangle. This is 30. This is 10 centimeters, which is 0.1 meters. So I can say that h is equal to x sine of theta because it's opposite the angle. And again, we want to practice doing this in terms of variables because a lot of times now on the AP test, everything's in terms of variables. So you don't want to just substitute in numbers. So what happens at this point? So here we're going to say UG naught plus US naught plus K naught is equal to UGF plus USF plus KF. Now before we start substituting in, we're going to say is anything 0. So we're going to say it's not moving in the beginning. And then here, because it goes down to whatever I'm going to call base level, I'm going to say this is 0. So at the top, we have mg h naught, because the spring's not compressed or stretched, is equal to 1/2, because then the spring, when it moves down, ends up stretching, 1/2 kxf squared plus 1/2 mvf squared. Now this h naught, I'm going to have to substitute this in. And the reason I'm doing it step by step is because what if this was in terms of variables? You need to know how to do it. So I'm going to have mg, and then I'm going to say x sine of theta is equal to 1/2 k xf squared plus 1/2 mvf squared. Now because I'm solving for vf, because it says determine the speed, I want to make my algebra look a little nicer. To get rid of this 1/2, I would multiply everything by 2. So now my next step is going to be 2mg x sine of theta is equal to, and let me just go ahead and subtract that from the other side, minus kxf squared is equal to mvf squared. So what I'm going to do is I'm going to divide by n, and since I want to solve for vf, I need to take the square root of both sides. So let's kind of simplify a little because I'm going to run out of paper. So it's 2 mg x sine of theta minus k xf squared over m is equal to vf. So now I'm going to substitute in my values. 2 times 7.2 times 9.8. Normally I would write the units, but I'm kind of squished here. Times sine of 30 minus 300 times 0.1 squared divided by 7.2 kilograms. I should have written smaller. So when I do all that on my calculator, VF comes out to be 0.751 meters per second. For part B, that was part A, it says find the maximum displacement of the spring when it's fully stretched. So now maybe it went all the way down, because before, you know, you can do conservation of energy between any 2 points. So now I'm going to do maximum displacement. So I'm going to choose the bottom here to be 0. So again, the total energy before is equal to the total energy after. So I can say UG naught plus US naught plus K naught is equal to UGF plus USF plus KF. So at the bottom, I know H is 0, and I also know, so at the bottom here, my H is 0, and then also, if it's not moving, my kinetic energy is 0. Okay. So this goes to 0, and this goes to 0. So this is what I have left here, and at the beginning, it's just the gravitational potential energy at this point. So this goes to 0, and this goes to 0. So what I have here is I have mgh naught is equal to 1/2 kx squared. I'm going to substitute that in. I could have done it at the beginning. Mg x sine of theta is equal to 1/2 kx squared. So I would rearrange the equation to solve the unknown in terms of the known. So what I can do first off is I can factor out an x from each side. Okay. And then I'll then multiply both sides by 2. So I'm going to have 2 mg sine of theta, and then I'll divide by k is equal to x. So now I'll substitute in my values. 2 times 7.2 kilograms times 9 9.8 meters per second squared times sine of 50 degrees over 300 newtons per meter. So when I do all that on my calculator, it comes out to 0.235 meters. Now remember, in physics, you always have a foolproof way to check your work every time by carrying your unit through. So I should end up with meters. So a kilogram meter per second squared, that's a newton, divided by a newton over a meter. So a newton divided by a newton over a meter is a newton times a meter over a newton. So the newtons cancel, and I end up with meters, which is my correct unit for X. So I say I didn't make a mistake. That's it. So they look worse than they actually are. Okay.